Alright, so what I want to discuss in this short video is the compression of gases. And more specifically, we want to determine the work of compression. And if you remember the differential form of the mechanical energy equation, there's that term dW, which is basically the work of compression in its differential form. Alright, if you want me to remind you the entire equation, which we saw earlier, it's the basically engineering Bernoulli equation which was written as 1/2 alpha times V2 square minus V1 square bar. So that's those two terms here represents the kinetic energy, and we have our potential energy G Z2 minus Z1, and we have a work of compression. So work of compression, in this case, that will be written as dP over rho from station 1 where we have P1 to station 2 where we have P2, and there can potentially be some shaft work and of course friction forces. And what we're going to look at right now is just that term, which is the work of compression. So we're going to assume, we're going to drop the other terms, all right? We're just only going to look at the work of compression, dW. So how we integrate dW, and how we determine the work of compression is going to depend on whether our compression is isothermal Isothermal means that there's no change in temperature, or adiabatic means that there's no heat changes, so basically no heat transfer, or it can be polytropic. So polytropic means that potentially there can be changes in temperature, there can be heat exchanges, etc. So it's more like a general case. All right. So let's get started with the isothermal compression. All right. So let's label it as A, isothermal compression. So that we're first going to recall the law of the ideal gases. So that law of the ideal gases is PV equals to nRT. And so, well, you know that N equals to M over M. And if you write the mass density as the ratio of the mass to the volume, then you're going to end up with something like P over rho equals to RT over molecular mass. And that's going to be a constant for an isothermal compression. All right, so isothermal compression, P over rho equals to constant. All right, so now we're going to use this to integrate dW. Okay, so dW, so let's just write W. That's going to be equal to the integral from P1 to P2 of dP over rho. And in this case, we're going to change rho to, well, its expression as Pm over RT. Okay, so that's the same as W equals to, so here we have P1 over P2 dP And now you change rho to its expression as Pm over RT. Okay, so here you use basically the expression that we just established as rho equals 2Pm over RT. Okay, so now we take out the constant terms from the integral, which is simply going to give us W equals to RT over M and the integral of dP over P between P1 and P2. All right, and so well, this integral is pretty simple after, pretty straightforward. It gives you W equals to RT over M, the log of P2 over P1. And finally, we've seen above that RT over M was a constant. So we could also write it as, let's say, RT over M equals to a constant, and it could be the ratio of P1 over rho 1. It could also be the ratio of P2 over rho 2. Basically any pressure as long as it's associated to the density at the given pressure. So let's write eventually a result as P1 over rho 1 log of P2 over P1. And that's going to be a work of compression for an isothermal compression. Okay, now we're going to move on to the second case, and let's add a page to it. All right. Our second case will be when we have adiabatic compression. Adiabatic compression. So if you have adiabatic compression, then in this case, the relationship that we have for the gas is like, with respect to the temperature, the molecular weight is no longer P over rho equals to mR over T. It's no longer a constant, but P over rho to the power of gamma equals to constant. And gamma is the ratio of the heat capacity at constant pressure to the heat capacity at constant volume. Okay, heat capacity at constant pressure heat capacity at constant volume. Now let's get back to a work of compression. W is still the integral between P1 and P2 of dP over rho. And so this time we have the integral between P1 and P2 of dP divided by P by the ratio of P over the constant to the power of 1 over gamma. All right, and that's because of the relationship that we just established, that for an adiabatic compression, P over rho to the power of gamma equals to a constant. Okay, so from there, we're going to basically do the same, take out the constant terms of the integral term. It's going to give us W equals to, this time, the constant to the power of 1 of gamma, and the integral between P1 and P2 of dP over P to the power of 1 over gamma. All right, and then, well, that constant, like we did for the isothermal compression, it could be, let's say, P1 over rho 1 over gamma. It could also be P2 over rho 2 to the power of gamma, etc. And we're going to keep P1 over rho 1 to the power of gamma, giving us P1 over rho 1 to the power of gamma Alright, and the whole thing, of course, to the power of 1 over gamma. Let's not forget that. And there we still have our integral between P1 and P2 of dP over P to the power of 1 of gamma. Okay, so we can slightly simplify things now. So that's going to be P1 to the power of 1 over gamma over rho 1. And there, let's say we have P1 over P2, and we're going to integrate P to the power of negative 1 over gamma dP. Okay. And then, well, we can start the integration work, giving us P1, 1 over gamma, divided by rho 1. So there, we're going to have 1 divided by minus 1 over gamma plus 1, and our P is going to be to the power of negative 1 over gamma plus 1, and it's going to be evaluated between P1 and P2. All right, continue. Giving us, so here still P1 to the power of 1 of gamma divided by rho 1. Then we have that constant term in front of the bracket giving us, so here you've got minus 1 over gamma plus 1, giving you gamma minus 1 over gamma. So we can simply write it this way. And there we have this evaluated already, P2 to the power of minus 1 over gamma plus 1, and minus P1 to the power of negative 1 over gamma plus 1, like that. Right, and so we could basically stop here actually, or we can make it slightly more beautiful, doing like that. So we're basically going to divide all the terms in the bracket by P1 to the power of minus 1 over gamma plus 1. Okay, so that's going to give us, so here we take P1, gamma minus 1 over gamma, and there we're going to have P2, gamma minus 1 over gamma, divided by P1, gamma minus 1 over gamma minus 1, like that. Okay, and from there, we can finally slightly simplify the expression, since we have in front P1 to the power of 1 over gamma, and in front of bracket we have P1 to the power of gamma minus 1 over gamma. So basically the powers disappears, giving us W equals to P1 over rho 1 times gamma over gamma minus 1, and times P2 over P1 to the power of gamma 1 over gamma minus 1. And that is the expression that we were looking for the work of compression in the case of an adiabatic compression. And finally, that's the last case. If we have a polytropic compression, then in this case, we have P divided by rho to the power n equals to a constant. And you will note that n equals to 1 if you have an isothermal compression, then you will have n equals to 1. And if you have an adiabatic compression, then you will have n equals to gamma. Otherwise, well, basically n would need some experimental measurements to be able to basically to find out its actual value, its exact value. And well, you do the exact same integral work as for the adiabatic compression, right? The only thing that you're going to change is gamma to n. So I will just simply write the final result. We have W equals to P1 over rho 1, and here you have n over n minus 1. And there you will have P2 over P1, n minus 1 over n minus 1. Okay, so that's the exact same work as in the case of the adiabatic compression. That's the same integration. And that's it for all work of compression in the case of compression of gases.